Good morning. Yeah, there are a few of you out there. Thanks for coming. Thanks for staying around and coming to this session. My name is Kevin Farley. I'm a principal program manager in the data platform team. I've been in the SQL group for about 14 years now. I'm going to be talking this morning about SQL Graph, so the graph enhancements in SQL Server and Azure SQL Database that we've been adding over the last couple years, and the enhancements that we're making that will be shipped on-premise in SQL Server 2019. They're in preview now, and will be coming in Azure SQL Database a little before that. So if you're expecting something else, this is what we're going to be talking about. So just to set a level playing field, if you will, how many people know what graph databases are and what graph processing is? Okay, so we're going to go over some of the basics, and if you've been through this before, I apologize, but I think it's important that everybody has the right groundwork so we can see the rest of the features and understand. So what's a graph? A graph is a collection of nodes and edges. Okay, what's nodes and edges? A node is an entity, a customer, a supplier, a product, lots of different things. It's an object. And edges are connections between objects, and more importantly, the relationship between objects. So for example, a customer can purchase an object, a product. So that purchase would be the edge between customer and product. So both nodes and edges can have properties. Obviously, an object, a node, can have properties. So a product has a lot of different attributes to it. But unlike the concept of like foreign key, for example, the connection between objects, between nodes and edges, between nodes and nodes, which are called edges, can also have properties. So in this instance, bot would be the node between customer and stock item, and it might have a quantity. It might have a price. There's a lot of different, a date, lots of different attributes you could have there. But the idea is there that you can have a richer bit of information. You can understand what's happening that way. So what's a graph database? Edges or relationships are first-class entities. It's not a second class like hierarchy ID or foreign key, or maybe even you could think of junction records as a second class, but these are first-class elements in the database, and they bring a lot of richness and a lot of capabilities to graph processing, which you'll see when we get into some examples. The other thing that's interesting is that an edge can flexibly connect multiple different nodes in a graph database. So you might have nodes for products, houses, different classes of things, and the same bot edge could connect a person to a house, and a person to product, a person to something else. So it doesn't have to all be the same object type, same node type on either end of the edge, unless you add constraints, which we'll talk about in a bit later. So you can express pattern matching really easily, and multi-hop navigation. The whole thing that Graph makes possible is you can express these relationships in your queries really simply and flexibly. It makes it very intuitive to understand what this query is going after and how you might extend it to different situations. Because it's all built into SQL Server, it supports OLTP and OLAP queries just like any other tables. So why a graph database? You might have hierarchical data, and hierarchical data generally is a nice tree structure, but reality is generally not that clean, right? There's exceptions always. So if you're using something like hierarchy ID, that works perfectly if you have a very clean tree. But a node in a hierarchy structure can't have two parents. In this case, it's an org chart where one person is managed by their direct manager, but also has a dotted line to another manager. That's I don't know how you would do that with hierarchy ID. So that's one of the things that graphs can do. They can make those relationships very simple. You can have complex many-to-many relationships in your schema. Foreign keys, you can only model one-to-many relationships. You can't do many-to-many. So the typical relational way to do this would be to create a junction record. And that is functionally possible. You can do that. But it gets really complex really quickly. When you start getting multiple hops involved, your query gets really dense and not that easy to parse for humans. SQL can parse it, but for me, if I walk into this big, massive T-SQL, it's harder to really get the idea of what's being gone after there. And then being able to tune that query becomes problematic because the more complex the query is, the more difficult it is to get it properly tuned and performing right. And finally, you want to analyze interconnect data relationships in your applications. So you can draw inferences from relationships that exist between the different entities in the graph. For example, Alice and Bob are from a given location. You can find that by the from edge. Both Alice and Bob are friends of each other. Okay, so now you know there's a relationship between these two people. Alice bought a product and recommended it. There's a good chance that Bob, being Alice's friend and from the same location, might be interested in that same product if Alice likes it. So that's how a lot of the product recommendation engines work. It makes it really easy to get inferences out of information that might not be obvious on the surface. Make connections between different entities on your graph. So why are we adding graph capabilities to SQL Server and Azure SQL Database? Our approach is simple to embrace and extend. So we're taking the existing SQL product and extending it. How many people would have preferred if we had made a completely different database for a graph and have it separate from the SQL database? So in general, people would like to have a single product that can capably do multiple tasks than having to have separate products, separate databases, so you can't necessarily talk to the information. The nice thing about graph is that you can interrelate the graph elements with the rest of your database. You can just join them across each other and get access to all of that data in addition to the richness of the graph. So with SQL, we've got a very mature platform. There's 40+ years of academic industry research behind relational database in general. SQL Server has been around for 29 years, regardless of what that flyer going around was. It's a very highly evolved ecosystem, lots of tooling and community support, so that it's a very rich environment to drop the graph capabilities into, rather than starting from scratch with something that has no support. It's a trusted platform. Lots of corporations put their mission-critical data in SQL Server, so it's a very capable platform that is already trusted by a lot of organizations. I'll take a little bit of time here to talk about this piece. This gives you the ability to have the same solution in the cloud, on-premise, or back and forth. So what do I mean by that? With SQL, we have one code base. There's not a separate code base for Azure SQL Database and SQL Server. Something like 12 years ago, we did fork it and there was a separate code base, but it's been together for a good 9 or 10 years. So there's all one code base. We refresh the bits in Azure SQL Database about once a month, and about every couple years, we'll ship the current state of that code tree out to the on-premise world as SQL Server. But it's all based on the same code. So that means there's really nice compatibility between Azure SQL Database behaviors and SQL Server behaviors, because it's all built on the same code. There are certain behavior differences, just like if you load a standard edition key, you get one set of behaviors. If you load enterprise, you get a different set of behaviors. When we deploy in the cloud, we get a different set of behaviors, but it's all based on the same core logic. We made the call back in SQL 2016 SP2, I believe it was, that any feature which impacts programming surface area will be available in all SKUs. So there won't be any surface area differences. The differences have to do with perf and scale between the different levels. So by putting the graph capabilities within SQL, the SQL platform, you have access to them whether you're deploying on-premise, in the cloud, or whether you're shifting applications back and forth. It's a very fluid environment. Are there any questions about that? Is that a hand or just, okay. And it's backed by research. I mean, there's a lot of research going behind the relational platform as well as the graph pieces that we put in. So I'll start with the graph extensions we added in SQL 2017. SQL 2017, just like you can create a relational schema, you can create a graph schema. You can create a graph's a collection of nodes and edge tables. Since we're adding graphs capabilities into SQL, it was natural to represent them internally as tables. And this means you can do interesting things like treat them as tables within queries or treat them as nodes and edges within queries. And you can join between nodes and edges even in a graph query and then join that to other relational tables to get access to other data which doesn't make sense to be in a graph. We added some language extensions. So we added DDL extensions to be able to create node tables and edge tables, as well as query language extensions. There's a new match built in, which is what evaluates the graph so pattern matching. So there's a style of writing relationships and queries in graph called ASCII art, which I'll show you how that works later. It makes it very intuitive how you're looking for that relationship. And the match predicate evaluates those and turns that into the execution on the back end. It's built into SQL Server, so it's got the backing of the whole tooling ecosystem that you're used to with SQL. So everything you're used to, you backup, restore, SSMS, all that just works with Graph. So in the SQL engine, you have, wake up my laptop here. Okay, that's not coming up. Why is that not coming up? Okay. So you'll see over here on the left that we've got, in addition to the user tables, the system tables, there's now a section of graph tables. You'll notice that you've got the typical table icon, but in addition, it's got that little blue dot in the corner. And that dot signifies that this table is a node table. Similarly, down here, you've got another table that has two dots connected, probably an edge table. In fact, that is an edge table. So this is just an indication that we have deeply integrated the graph capabilities into the tooling, into SSMS and the other tooling. So existing tools work out of the box. SSMS, backup and restore, import, export. You can join existing tables with graph nodes and edge tables. All the features that you're used to within the database, column stores, machine learning with R and Python, HA, et cetera, all work with graph tables because it's just, in some senses, it's just another table within the SQL database. It just has extra query processing capabilities built in to do the graph evaluations. Dynamic data masking, row-level security, all that works with graph tables. And of course, it's SQL Server. It's available in both Windows and Linux. How many of you have explored SQL in Linux? Okay, a few of you. One SQL on Linux was first announced, a lot of people came at it with the idea that this was going to be some small subset. It wasn't going to be the full-blown product. But in fact, it is. There's always been a layer in SQL that was called SQL OS, which was the interface between the SQL product and the operating system it lived on. We took that component, SOS, and factored out the pieces that were actually specific to an individual operating system and made 2 implementations. So there's one implementation if you're running on Linux that gets linked in. If we're building for Windows, it's the other version that gets linked in. Everything above that is the same code. So behavior is going to be the same. Performance is the same. Neither platform is going through any emulation layer. It's all native to the platform. We've run benchmarks, and they're just neck and neck. So SQL on Linux as well as on Windows. So the first extension, create node. And here you see familiar create table syntax, and you have as node. So that's how you create a node. You create this table with customers, whatever attributes you want, and as node tells you that this is going to be a node table. When you create a table as node, we automatically include an implicit column called $node ID. Node ID is how we do the linkage between nodes within a graph. So it's going to have the table name that it is, unique ID, which is the object ID of that table, plus a unique identifier for this instance within that. So you'll see that although it's stored as a big int, under the covers, it gets represented as a JSON string. So you have type equals node, schema equals DBO, table equals customers, and the specific ID is 0, 1, 2 for each row. Okay, so you get that. We also will implicitly create a non-clustered unique index on the node ID column. And the reason I bring that up is that while you're creating the node table, if you create your own index that indexes the $node ID as unique index, then we won't create the implicit one for you. So if you want more control over that index, you want to include some extra columns because you know it's, anytime I reference this, I'm also going to be wanting that column. You can have more control over the shape of that index. But you don't have to. We'll create it. That index on the node ID is what makes the graph processing efficient. So we have to create it. Create edge is very similar. Create table bot. So bot has an attribute purchase count. You don't have to have attributes there, but you can have whatever attributes you want as edge. An edge table, again, has a $edge ID, which has the same sort of format, but it will also have 2 other columns, which are $from ID and $to ID. And those show you which edges it's connecting. So here you see the $edge ID on the left side, which is the identity of this edge. And then the next one is the from ID, so that's the node that you're starting your connection with, and to ID is the node that the link is on the other end of the link. And those are basically just the node IDs. And then any included columns are out there to the right. You'll note that this is a directional relationship. So all edges are directional. They have a one-directional relationship. If you want to establish a bidirectional relationship, like Bob and Sally like each other, that's one edge going from Bob to Sally and another edge going from Sally to Bob. Sally might not like Bob, right? So that's the semantics here. Inserting data into graph tables. Inserting data into node table is just like inserting data into any other node, any other table. So insert into customers, customer name, etc. This is how we populated the customer table in the sample database we've got. Samples are all based on AdventureWorks. So inserting into an edge table is a little bit more involved because you have to get the node IDs of the from and to nodes that you're connecting with this edge. So insert into bot, $from ID, $to ID, and purchase count. So those are the columns within the edge that you're inserting into. And the values are select customers.nodeID and stockitems.nodeID, and then purchase count is a variable that you're using to populate this edge. From customers and stock items, where customers.customer ID equals customer ID, and stock items.stock ID, stock ID. So you're looking up the specific customer and the specific stock item that you want to link with this edge. You may already have visited those nodes and have cached the node IDs, in which case you don't need to do this specific query inside the select or inside this insert, but this is how you populate a node ID. Are there questions about how that linkage happens? Okay. Match. This is kind of the magic sauce, the SQL secret sauce in graph databases in general. You can have multi-hop, join-free matching using match predicate, ASCII art syntax to facilitate graph traversal. So this is what a graph query looks like. And I want to call your attention to the where match clause. Matches, as we talked about, the new intrinsic added. If you see that funny thing with the parens and the arrows and stuff, that's what we call ASCII art. And if you think about how you would write on a chalkboard that I want to get the relationship of customers that bought a stock item, between customers and the stock items that they bought, this might be how you would draw it on a blackboard, on a whiteboard. And so this is standard syntax across graph databases. So you have, so this is where match customers that bought stock items. So here you're going to get the customer name and the stock item name. So for each customer, you're going to see all the items that that customer bought. And where the stock item name equals all-purpose bike stand. So in this instance, what you're doing is you're filtering that down to all the customers that purchased an all-purpose bike stand. Does that make sense? Everybody still awake after last night? Okay. Product recommendations. This is where we start really getting some of the value and richness out of the graph capabilities. We're going to look at a simple scenario to see how graph processing can help you. It's a simple product recommendation scenario where a customer bought a stock item. The stock item was supplied by a supplier, and the supplier is from a location, and the customer is also from a location. Might be the same location, might not. A customer can be a friend of other customers. So with this, you can construct the relationship to understand. So customer A bought a stock item, and I want to know all the other things that this customer bought, and other friends of this customer who bought that stock item, what else did they buy? So you can get those sorts of lists. So if you're buying something on Amazon or one of those sites, when you put something in your basket, you're going to get this line on the bottom that said, people who purchased this also purchased these three things. They're doing very similar logic. May or may not have to do with friendship, but it might have to do with location, any other information Amazon happens to have squirreled away about you. They're going to find people that are as similar as they can to you and make recommendations based on that set of customers who also bought stock items. And this is a classic graph implementation. So you could do all this with straight relational data without the graph processing, right? Anybody have doubts about that? Anybody want to see what the query looks like? So that's what the query looks like. So you start with current customer and get the user ID and product ID of the product they're buying. From there, we find the other users who have purchased this same product ID. Once we have that list of other users, then we join that and try and find other items that those users have bought. And finally, we rank those by the top 10 other items and have our list of recommendations. Now this is functional, and it will perform okay. It's not a huge performance problem, but it is a huge maintenance problem, right? If you just walked up to that query, it would take you a few minutes to digest it and figure out what you're getting out of it, right? And if somebody said, okay, that's a great recommendation engine, but I want to recommend only products that are made by the same supplier, how would you extend that? It could be done. It's not impossible, but it's going to take a lot of head scratching, and it's going to make it even more complex and bloated, and then you get to tune it. So this is why we think we've got a better solution in Graph. And again, Graph is not us specifically, but this is why we think Graph is a good solution to this class of problems. So that's that same query as SQL Graph. So you're taking the top 10 recommended item.product name from products as item, so that's the first item that you're basing the recommendation on. So this is the item that the person purchased. Customers as C, so all the customers. Bought as bought other, bought as bought this. So, and then products as recommended items. So that's going to be a result set of items to recommend. The match clause, you start with C in the middle. So that's the customers. And going to the right, you're looking for customers that bought this item. Okay, that's similar to the query we saw before. So you're looking for the list of customers who bought this item. And then going the other way, you want to find for that list of customers what other items they bought by following the bought edge. This instance of the edge you're naming as bought other, and get the list of recommended items. That's all there is to the query. You're filtering it so that the item name that you're recommending isn't the same as the original item name, because that would be silly. And you're going to filter out the person who originally bought it. He doesn't have to recommend his own stuff. That's all there is. So it makes it a very simple and intuitive solution. So this is how we use the graph syntax to traverse this sort of relationships. And this is how you would extend it to limit it to a given supplier. So the stuff that's grayed out on the right is the query we had before. We just extend that by recommended products that were supplied by the same supplier. So it's very intuitive to extend the query and get more insights, more relationships, more value out of your queries. We also introduced in 2017 the merge syntax. So this is kind of the upsert scenario. So in this case, if you have an edge between two nodes, you want to update it. If the edge doesn't exist, so if those two nodes aren't connected by that edge, you want to create the edge. And so here you have has address, using address, AT, join customer on customer, join address at ID. On match, customer has address to the address. So the edge has address between the customer and the address. If it is matched, then you update set the street address to the one you're bringing in. If not matched, then insert values into the edge. So this is how the merge DML works. So you can do upsert scenarios with an edge, all within a simple statement. Any questions about that? Constraints. So just a plain edge can connect any two nodes. You might not want that. So for example, if you have an edge between person, edge called has phone, you might want to restrict it to connecting some node and phone number or contact information. So this is what the edge constraints can do. So in this case, the example is Bob has credit card, linking you, Bob, to a credit card. Credit card doesn't have Bob. It feels like that sometimes, but not technically how it works. Again, edges are directional. So here you have create table has credit card. You're creating the edge with a constraint, CHA, connection customer to credit card. So this edge can only connect customers to credit card. And on delete, no action. So if you delete Bob, it'll just leave the edge and the credit card orphaned. Right now, that's the only action that we support. You can expect that there will be other actions in the future coming that make sense, something like Cascade perhaps, something like that. So now you're enforcing the semantics, so you can't use has credit card to link Bob and his car. There's system tables that go along with this. So you have sys.edge constraints. So you have the columns inherited from object ID, all the common object ID sys.objects columns is disabled. You can have constraints that are enabled or disabled. Is not trusted. That edge constraint hasn't been verified by the system. So in other words, if you create a constraint on an edge, until the system verifies that the existing data satisfies the edge, it's not trusted. Delete referential action, which is a tiny int, and then there's the description, so that's the no action. And again, it's there because there will be other actions in the future. And is system named? So was the name generated by the system, or was it supplied by the user? Edge constraint clauses show what object ID to and from you're going to allow to be connected by this edge. So this is a clause number from ID and to ID. So you can have multiple clauses that says this edge can connect this object and that object or that object or that object. So you can have a fairly flexible set of connections that you'll allow, but it's restricted to that set. And sys.edge constraint clauses is how you find that. And then sys.objects has an object type that's EC for edge constraint. Something that's new, it's in preview in CTP 2.0 for derived tables in matched queries. So we're allowing you to have views or derived tables as participants within your match queries. So in this case, get Alice's contact information, phone, address, phone, social security number. So you have this view that is, you have a derived table here as all contact information. So select street as contact information from address, union all, select cast phone number as varchar 200 from phone number, union all, select cast SSN as varchar 200 from SSN as all contact information. And then you can do a match with all contact info. So this allows that. And this plays into the next demo, which is going to be about fraud detection. Has anybody looked into how you do fraud detection? A few people, good. So fraud detection is a very common graph scenario usage where we look at the relationships between people and find relationships that might not be obvious on the surface. For example, person A pops up with an extra $1 million. $1 million happens to be missing from some account that person A doesn't have any access to. Person B had access to it, but he doesn't have the money. It just happens that person A and person B meet at the club every night, along with person C, who ended up with the money ultimately. So those are the sorts of relationships you can find to uncover the fact that people may be collaborating. Obviously, that's not a smoking gun, but it's a lead. Let's look at a demo. The demo will see how we can identify fraudulent users and activities. So in this case, a customer has contact information, has an address, has a phone, has a social security number, multiple ways to identify a person. Social Security, no other person should have that Social Security number, right? Address, at most, a handful of people should live in that same address, and likewise, probably only he has that phone number if it's mobile. If it's a house phone, then probably only a handful of people are going to have that. If you start seeing many more people, then that's a red flag. Person has an account, has an unsecured loan with some amount of credit on it, and may have a credit card. So the way some fraud rings work is that a group of people will start collaborating, and they'll take real identification information, Social Security number, phone number, address, and just merge it together to create lots of permutations. So this person's Social Security number with that person's address and that person's phone, and just have lots of different permutations of that. In each permutation, they set up bank accounts, they set up credit limits, and have that going for some time, maintain all these fictitious identities. As the accounts are being validated, it's a real Social Security number, so it doesn't raise too many flags. They build up some credit rating and start putting lots of money on the credit cards, taking out unsecured loan. When they're ready to pull the trigger, they'll max out the credit cards, max out the unsecured loans, and then those identities disappear. So that's the kind of scenario we're trying to find here. So I'm going to show you how that looks. We're going to start by, I'm not going to actually drop these views and recreate them, but we have several views involved in this demo. We have retail.graph.creditinfo, contact info, has contact, and has credit. So we have one view that select address as contact info, union all, select phone number as contact info, and so you'll have the contact information data is either an address, a phone number, or a Social Security number. And then you have the contact info type, which is either address, phone, or SSN. So you have those informations. That's one view. And again, you have another view, which is has contact. That's an edge. So you select has address, union all, has phone number, union all, has SSN. So in other words, you can use that edge to find anybody that has any of those three elements. And then another view has credit card, or has unsecured loan. And finally, the view which has credit info, which is credit number, credit limit as risk amount, credit card as risk type, and account number, loan amount as risk info, unsecured loan from unsecured loan. So that's how those work. Now we have a graph query that'll help bring this all together. So what's this doing? We got a string aggregation. So for each element that satisfies it, we're going to aggregate this into a long string. So you have first name, last name, and a comma get added on for each element that satisfies the query. We have the count of first name, so the count of the people that satisfied it is the ring size. That's the number of people in the ring. Contact info as shared info, contact info.contact type as the ring type, retail graph customers, contact info, and has contact. So that's matching all the people that have the contact information. So your match is has contact and contact info, grouped by contact info and contact type. So what you're doing there is finding all the people that have the same contact type. There should only be a handful. Let's see how many there actually are. So 2, that makes sense. 209, not so much. So you see here we've got rings with hundreds of people sharing the same address. Those are probably going to be problematic. And now we can assess the financial risk associated with these fraud rings. So again, you're going to have the string aggregation, so you're going to build a list of names involved in the ring. The count of first name as ring size, so the number of people in the ring. Contact information as shared info. Contact type as the ring type, so it's social security ring, is it address, is it phone number that are being duplicated. Risk amount, the sum of the risk amount as the financial risk. So if you sum up all the credit outstanding for all the people in that ring, that's the risk for that ring. And the risk type. Retail graph where you're doing the match, so your customer's AH has contact information, has credit, and the credit info. That gives you the type of credit and the amount of credit. You group by contact information, so you're finding all the people that are sharing contact information inappropriately, and the contact type, and then the risk type. So you're grouping by unsecured loan or credit cards. Having count of first name, so number of first names greater than 1. Order by ring type and financial risk, descending. So again, we have a very large number of rings. Some of them are very substantial financial risks there. Ring size varies again. Lots of 1s and 2s, but which may or may not be actual fraudulent activity. But some of them end up being quite significant. So again, this is the top set of rings. Actually, those are 5,000 rings that were discovered in this data set. So questions about how all that worked? These lights made it hard to see you. Okay? Yes? So how do you keep the graph data in sync with your production data? Right. One option would be to make your production data a graph table. It's just another table in the database. So if you're frequently using it for this kind of query, you can do that. Or you can have a job that just syncs them periodically. Good question. Any others? Yeah. So the question is about setting up a graph, what needs to be done to set it up. You just create node and edge tables and start populating them.
Oh, no, I meant is to use the graph, I mean, out of the box, with SQL 2017 and above.
To use graph in SQL 2017 and above, you just,
Come with it?
yeah, it's just,
Any other configuration?
it's just more syntax we've added into the product.
Okay.
So you don't have to do anything special. It's all part of the product. That's kind of the SQL, the way we do business is that we just add new features to the product, and it's there. Yeah. So when to use a graph? Graph data and relational designs can answer similar questions, but traversal of relationships between objects, especially where the relationships may not be obvious, to find the primary applications, graphs can solve more intuitively and with less code. If you're looking at a lot of relationships, a lot of multi-hop traversals between objects. There's one other thing I want to show you here about that. Going back to the laptop here. So we've got a result set, couple result sets here with thousands and thousands of elements. How do you make sense of that? How do you visualize it? I created a quick Power BI screen that shows diagrams of financial risk. So this has a filter for social security number. There's only one pair of people that happen to be sharing social security number, which is an obvious red flag. but you can filter it down to phone number. Yeah, that's a few. Or out here, you can filter this to look at address, which even more. So there's different ways you can visualize this using Power BI and other related products. Okay? Questions on that? Right. So I mentioned that you could use column stores on the node tables. Can you also use it on edge tables? Certainly. So you can put column store indexes on the data within the node and edge tables just like any other table. You can also add whatever other indexes you want. They support all index types and all constraint types, node and edge tables. There's no restrictions on that. Yeah, it's just another table. So if you're doing a relational query across it, it's absolutely the same. The graph query is under the covers doing relational joins. A lot of that work. It's just you don't have to do the work. We'll do it for you. And that's why we make sure that we have those indexes. Question? I think the merge is new for 2019. So merge and constraint. Might be something I'm forgetting, but I think those are the main ones. Anything else? Yeah. So when you're doing a match, why can you only use ands and not ors for the other clauses within that query? You can. There's no restriction. It's just those queries happen to use the ands to filter down the result set. You could expand it with ors as well. I'm not certain if you can or two matches. I'd have to think about that. Anything else? Regular table can't be part of the match, but it can part of a query that contains a match. So you have a match to do the traversal between a set of tables and then join it to other tables.
The regular syntax.
Yeah.
And what's the point of the JSON?
It just makes it human readable. Otherwise, it'd be this big number.
Okay.
So internally, it's stored as a big int. It's a combination of object ID and the specific object number for that individual. Anything else? Good. Graph database scenarios, recommendation systems, we've looked at that, how those work. Fraud detection, we've looked at that. Content management, bill of materials, product hierarchy, customer relationship management, Internet of Things. There's lots of different applications where graph can be very useful in finding relationships that aren't obvious on the surface. It's a great what-if tool, and especially with the ASCII art syntax, you can just draw it out and say, let me see what the relationship is between these things, and hit the query and pop, there you go. So, with that, and I'm a little bit early, but I think I will end this here unless there's more questions. Yes? So since it's stored in the same database, can you have foreign keys that point from a regular table to a node table? Certainly. It's relational data. Other questions? Yes. So you can display things using tools like Power BI. SSMS has extensions built into it. Above and beyond the SQL tools, I'm not aware of what is out there at this point. There's a lot of graph data tools out there in the marketplace. Other questions? Okay, well, thank you for your time. I hope it was a good conference for you guys.